Starting with number 31, each D subshell can accommodate a maximum of 10 electrons. Remember, the D subshells are these guys right here. And if you count the elements, there are 2, 4, 6, 8, 10 elements. Two can be represented in each orbital. And so there's a total of 10 electrons that can fill. Each P subshell can hold a maximum of 6. Each S can hold 2. So if you're unsure about that, remember these are the P's right here. Count the elements, there's 6. Count the elements right here, there's 2. So 2, 10, and 6. Good to go. The electron configuration of calcium. So calcium right here. Start from the top. 1s2, 2s2, 2p6. That gets us to here. 3s2, 3p6, and then this would be 4s2. So match that up right here, and I believe that is letter D. What is this the electron configuration of? So look at the ending part. So start here from argon and then work forward. So we have 4s2, and then we have 3d10, so it fills this, and then 4p3, 1, 2, 3, that would be the element arsenic. Let's see, moving on to number 36. Fe plus 2 atoms are represented by, so you notice it's got a little plus 2, which means it has 2 less electrons than it would normally have. And remember, when it forms ions, it's always the S and P electrons that are lost first. Now, if you have no other choice, then you could start to take D electrons away. But the S and the P electrons are the valence electrons, so those are the ones lost first. So normally iron right here would be argon, and then it would be 4s2, and then 3d, 1, 2, 3, 4, 5, 6. Remember, it's 3d6 because the D sublevel is always 1 energy less than the principal quantum number right here. So since we lose 2 electrons because it's Fe plus 2, these would be our 2 electrons that are lost. So we'd be looking for argon 3d6, which I believe is E right here. Which of the following atoms is the smallest? So the atomic radius, radii, trend on the periodic table is that they increase as you go down, and they increase as you go to the left and have less effective nuclear charge being experienced by the electrons in the highest energy level. And so we're asked which is the smallest, so we want the opposite of that. And so neon over here would be the smallest, letter C. It would be the furthest to the right and the furthest up. How many bonds does a carbon atom normally form? So carbon has 4 valence electrons. If you draw the Lewis dot structure, it would have 4 dots around it, and so it very, very much so likes to form 4 bonds. How many bonds does an oxygen atom normally form? So oxygen right here has 6 valence electrons, and it usually loves to have 2 unshared pairs of electrons, and so it goes out and forms 2 bonds. That's what it normally likes to form. Number 40, given the bond energies, calculate delta H for the gas phase reaction. And we're given several bond energies here, a OO, an OH, and an HH. Make sure to draw the Lewis dot structures of these, so then you make sure to include all the bonds. So for 2H2, it would be 2 HH bonds. And then for O2, it would be an O double bond O right here. And then for H2O, remember it's 2, and then H2O looks like this. And so we'd actually have 4 OH bonds in there because there's 1, 2 times 2. So it's bonds broken minus bonds formed, and this equals the enthalpy for the reaction. And the bonds that are broken are the HH. So our HH bonds are 436 multiplied by 2 because there's 2 of them, plus an OO double bond, which is 495. Nice hint they give you. They only give you the OO double bond. So if you thought of drawing oxygen as OO single bond, just look at the data they give you and you're like, oh yeah, I guess it's got a double bond. and then minus the ones that are formed. And so we're forming 4 times these OH bonds, which is 463. And let's see, we do the little math here. Oh, I guess they give us the math here. They don't tell us to do the actual answer. I think this ends up being D. 41, a sample of gas occupies 12 liters at a pressure of 1 atmosphere. What volume does the gas occupy if the pressure is changed to? So organize your data: initial, final, pressure, volume, temperature, and has 12 liters at a pressure of 1 atmosphere. What volume does the gas occupy? So I don't know. If the pressure is changed to 0.5, and we're going to assume that temperature remains constant. So you can notice that we've got the vice president relationship right here. The pressure goes down, so that means the volume's got to go up. So 12 liters times a ratio to make it get bigger, and your choices are 0.1 over 1 or 1 over 0.5. Which one's going to make it get bigger? Hopefully you chose the one that is the larger fraction, so 1 over 0.5. And we end up with 24 liters. Number 42. A sample of gas occupies 1 liter at 50 degrees Celsius. What is its volume at 100 degrees Celsius? So let's just use the same organization right here. Initial, final, here's our pressure, here's our volume, here's our temperature. Occupies 1 liter, 50 degrees Celsius, so 50 plus 273. And what is its volume at 100 degrees Celsius? So 100 plus 273. And then we're going to assume that pressure remains constant in this case. So for this one, this is the volume temperature relationship, or the TV, I'm sorry, I usually write it this way, TV relationship. One goes up, the other one goes up. So we know to multiply by a ratio that makes it go up, because this is getting bigger, obviously. So we have 323 right here, and we have 373 right here. So 1 liter times a ratio to make it get bigger. And the bigger one would either be 323 over 373 or 373 over 323. Which one would make it get bigger? Hopefully you pick the one with the larger number on the top if you want it to get bigger. If you're not sure, multiply by both and then find out which one makes it get larger. So when you multiply by that, you end up with 1.15 liters. More in the next.